Hello everyone. Today's topic is secondary structure prediction. So as you know that there are different levels of protein structure. So we have primary protein structure where the amino acid sequence of protein is present, right? Then these amino acids they form the secondary structure elements which are very important for the protein folding, which ultimately leads to the formation of a tertiary structure of the protein. And the further assembly we have a quaternary protein structure. So what is secondary protein structure prediction? So it is nothing but you have a protein sequence, right? So you predict how this protein sequence can conform into a particular secondary structure, whether it can be coils, alpha helices, or beta sheets. Secondary structure prediction is important, especially for tertiary structure prediction, right? And as you know that tertiary structure of the protein correspond to the function of protein. So you can also predict the function of the protein by predicting the secondary and then tertiary structure of the protein. So what are various methods for protein secondary structure prediction? So we have some statistical methods such as Chow-Fasman method and Gore method, and we also have some neural network methods. So first one is Chow-Fasman method. It was given by Chow and Fasman back in 1974, and this method is basically based upon calculation of statistical propensities for some residues which can either form alpha helices or beta sheets. So you'll be predicting whether a particular residue is present in a alpha helix or in a beta sheet. So in this way, for all the residues, you'll be having predictions whether they can form alpha helices or beta sheets. For example, in this case, we have these residues which are strong predictors of alpha helices, and proline and glycine, which are alpha helix breaking residues. Further table of predictive values is created for alpha helices, beta sheets, and loops or coils. And then you have these structures with greatest overall prediction value. All right. So if the value is more than 1, then you can say that this particular residue falls into a particular conformation, whether it can be alpha helix or a beta sheet. So how to calculate statistical propensities, right, for a particular residue? So it is given by this simple formula: propensity. For example, in alpha helix, the propensity is given by the percentage of residues in alpha helix. For example, I residue, it can be any residue, right? For example, alanine, right? So percentage of residue I in alpha helix. So in a protein there can be several alpha helices, right? So the residue percentage in all the alpha helices divided by percentage of all the residues in a alpha helix, right? So how many residues are there in a particular alpha helix? So this will give you a propensity of a particular residue, that is I, in a protein data set. Further, these values can be calculated as percentage of residue I in alpha helix by n alpha I divided by capital N alpha Ni. So what are these values? N alpha I is number of residues of type I in alpha helix, and capital Ni is number of residues of type I in the whole data set. And further, percentage of all residues in alpha helix, right? So remember, we are calculating the propensities for alpha helices in this case. It is given by n alpha by capital N. So n alpha or Na, you can say, is total number of residues in a alpha helix, right? and total number of residues in the whole data set is n. This can be easily understood with the help of an example. You can see here we have this particular protein sequence, and the first line corresponds to the protein sequence, and the second one is the secondary structure assignment for this particular sequence. So residues forming alpha helices are highlighted in red color. So in total there are 153 residues in this sequence, and there are 115 residues which are forming alpha helices. So we take example of alanine propensities. So how to calculate alanine propensities? That what are the chances of this particular residue, which is alanine, of falling in alpha helix. So if you remember, we have the propensity of alanine. So here the percentage of alanine residues in the alpha helices divided by percentage of all the residues in alpha helices. So first is percentage of residue alanine in alpha helices. How it is given? So we calculate this particular value, that is number of alanines present in these highlighted residues. So if you calculate number of alanines in the red colored residues, there are total 15 alanine residues. And if you calculate the alanines in all throughout the sequence, so you'll have 16 alanines overall. So the percentage is calculated by this is simple equation. So 15 divided by 16, you'll have 0.94. And next is percentage of all residues in alpha helix. So we know that there are total 115 residues which are highlighted in red, which form alpha helices, and there are total 153 residues. So if you divide these values, you have a value of 0.75. So the propensity of alanine, which is given by percentage of residue alanine in alpha helix and percentage of all residues in alpha helix. So simply divide this 0.94 by 0.75 obtained here. So you have a value of 1.25. So as the value is greater than 1, so this alanine is a strong alpha helix forming residue. We know generally proline and glycine residues are alpha helix breakers. So how about calculating the propensities of glycine in this case? So after calculating the glycine propensities in this manner, we have this value of 0.66. So it is less than 1. That means this glycine is not preferred in a alpha helix conformation. In this example, we have taken only one residue, that is alanine, and similarly these propensities can be calculated for all 20 amino acids in the protein sequence, right? And these propensities were calculated by Chow and Fasman, and they created this set of parameters or table of parameters for all 20 residues and their preferred conformations, right? So they assign these propensity values for alpha helices, beta sheets, and then you have these PT means the turns or the coils, you can say. So overall, based upon these propensity values, we can classify each residue into different classes. For example, we have strong helix or beta strand formers. We have weak helix and a strand former, right? We have indifferent, weak helix or strong helix breakers, right? So these are different classes of the amino acids based upon the propensity values which were obtained by Chow and Fasman. There are some rules for identifying alpha helices based upon Chow and Fasman method. So there can be different values assigned to these different parameters. For example, we have classified the amino acids into different classes. So we have strong helix formers. They are given this value of 1, and weak helix formers are given a value of 0.5, and other helix breakers are given a value of -1. So this method considers a window of 6 amino acids. So 6 amino acids will be considered at once, and the score based upon this classification is calculated, and if you have scores of greater than 4, then those residues are the part of a alpha helix. So at least 4 helix formers have to be there. So among these 6 residues there have to be 4 helix formers and not more than 1 helix breaker residue. So as soon as you have this score of greater than 4, then this site is called as a nucleation site. So after you identify the nucleation site, this window is extended and in both directions until the score is less than 4. So until you obtain a score less than 4, then you keep on extending the window and calculating the score until it becomes less than 4. So here is an example of a rule for identifying a helix. So suppose you have this amino acid sequence, and then how the program works, you will start considering right from the first residue, and you will select a window of 6 residues, for example 1, 2, 3, 4, 5 and 6. So you have a consensus of KVFGRC. So here we go, KVFGRC. So you'll be calculating the scores for this particular stretch first. So here are the scores. If you calculate the scores, so these scores are based upon the table which we discussed here. So you can take these value. For example, strong alpha helix formers will be given a value of 1, weak formers will be given a value of 0.5, and the breakers will be given a value of -1. So you have this type of values here. So if you calculate the score for first stretch, you have 1.5, which is not enough because we need a score of at least 4 or greater than 4. Then similarly we skip one amino acid, we start from the second, so that it includes another extra residue. So in this way we have VFGRCE. VFGRCE. So again we calculate the scores, we have 2, and similarly we start skipping one by one until we reach this particular stretch, which is RCELAA. So if you calculate the scores, it has a score of 4. So this stretch will work as a nucleation site for your predictions, and then you start extending this nucleation site until you get a score less than 4. So you can see this green one is the extension here, and the extension stops as soon as a glycine residue appears here. For example, KRHG, KRHNG. If you calculate the scores, the value is less than 4, 3.63. That means this is the end of the alpha helix here. So in this way you can recognize that your alpha helix starts from the residue R and ends at residue H here. So this is simple way of identifying the alpha helix by Chow-Fasman method. Similar rule can be used for identifying beta strands. So the values are assigned based upon strong beta strand formers. You have the value of 1, weak formers will have 0.5, and the strand breakers will have a value of -1. The difference is that the window which we use for scanning is only 5 residues. It was 6 residues in alpha helix predictions. Here we have 5 residue window, and the score is not 4, but it should be equal to and greater than 3 in this case. So at least 3 strand formers have to be there and not more than 1 strand breaker residues have to be there. And extend the length in both directions once you find this nucleation site here, and until the segment has the average propensity of less than 1. And continue the search and locate all the strands in the region in the sequence. So you can apply these rules throughout the sequence to identify the alpha helices and beta sheets. And if the residues they don't form alpha helices or beta sheets, they should be the part of the coils. So that's how this Chow-Fasman method works.